Okay, hello guys. Let's finish up the chapter 2, part 4 on Zener diode. Alright, there are many types of diode. We have touched a bit on this in the class last time. We have junction diode as usual that we have learned, the one that we are used in the lab exercise. And then there is a Zener diode, tunnel diode, Schottky diode, varactor diode, and so on and so forth. And I'm not going to touch the rest of it because there will be a subject on that uh, specific diode. All right. Um, Zener diode. What is Zener diode? It's a semiconductor diode, obviously. And major application is the voltage regulator. It will provide stable reference voltage for use in power supplies, voltmeter, etc. Zener diode maintains a nearly constant DC voltage under proper operating conditions. Okay, the symbol is like this, like a diode, but with this slightly curvy side. If normal diode is just a straight line, but this one is with a slightly curvy or with some tail on the symbol. Basic configuration of the network, for example, as this one. Okay. B in and we have R and then RL and then there's the Zener diode. Okay, we will see how this thing works after this. Analysis of Zener diode. The state of diode must be determined by followed by a substitution of the appropriate model. Okay, so as in forward bias, and when Zener diode is on, it will be like a voltage supply. When the Zener diode is off, it will be like an open circuit. All right. How does it work with when it is on, and how does it work when it's open circuit? We'll see that after this. Right. What's one special thing about Zener diode? It works at the breakdown voltage. Okay? When the breakdown happens, then the Zener turns on. Zener diode used as a current limiter due to its characteristics. Okay, used as voltage regulator, not voltage stabilizer. Right, this is what this is. If you notice, this is looks like a normal diode characteristic curve. If it's in forward bias, it goes curvy like that, exponentially upwards with this value of if it's secant, it's 0.7. Okay, and under reverse bias, there is a condition where the VBR, the breakdown occur. When the breakdown occurs, it will have like surge currents flowing. But then the one special thing about Zener diode is that it's reversible, meaning after a breakdown, when the voltage is reduced, then it will come back to as usual diode. But if it's just a normal diode, once breakdown, then it's breakdown. It's no longer work as back to its normal. So this is the special thing about Zener diode. Right, analysis. We do two type of analysis. VR with no load and VR with load. Okay. Uh, okay. Voltage regulator with no load. So this is the V in, and then RS series voltage, and then V out. VZ. Assume V in varies from VI minimum and VI maximum. Okay. We have this equation. We wanted to determine the power maximum dissipated. V in, according to Kirchhoff law, V in minus I Z RS minus V Z equals to 0. Okay. Why do we call this IZ? Because because the Zener diode is having a constant a current through it, and without the load, the current will go through here, and there's no going to the load. So this is the same current IZ throughout the circuit. So we have this circuit with the Chap voltage law equals to 0, and then you can find IZ equals to Z. Sorry, V in minus Vz over Rs. Okay, finally P equals to I times V power dissipated equals to Iz maximum times Vz. Okay, why do we look into Iz maximum? If you want to look at the maximum power dissipated, then you have to look at the Iz maximum. Alright, now let's look at the voltage regulator with the load. Okay, there are three conditions: V in, and RL are fixed. And then we have fixed V in variable RL, and also we have fixed RL variable V in. Okay, let's look at the first case. V in and RL are fixed. Step 1, we have to check the state of the Zinter diode, remove it from the network, and calculate the voltage across the resulting open circuit. So what it means here is we do KVL over there. If we do KVL here, it's actually basically a voltage divider. Okay. If you notice voltage divider is V out equals to V in times RL over RL plus R. Okay, if you are not sure, you can use Kirchhoff voltage law. This is open circuit. Okay, why it is open circuit? Why is it open circuit? Because we need to check the output voltage when the Zinter diode is off. What it means by off? When the voltage less than V in less than Vz, the diode, the Zinter diode is working as if like a normal diode, no current passing through, so it opens like it acts like an open circuit. All right. Step 2, substitute the appropriate equivalent circuit and solve for the desired unknowns. All right. Now, why do we in the step 2? Why do we assume that this is a voltage? Okay, this is due to the function of the Zinter diode, or the property of the Zinter diode. When the V in is equals or greater than or equals to Vz, then this Zinter diode will act like a voltage supply, whereby it will maintain. So if V in, let's say if Vz equals to 5, so V in equals to 5, then Vz will also equals to 5. Both. If V in equals to 6, Vz equals to 5. Okay, V in equals 7, Vz equals to 5. So what it does is to maintain the output voltage. Okay, this is the special characteristic of the diode. Alright, now let's look at this when the Zinter diode is on here. So we have Iz and IL. So we have to make use of this equation. Vz equals to VL, okay, like this. So we use Kirchhoff current law basically. Iz equals to IR minus IL. Okay, or initially you can have IR equals to IL plus IZ. So we are looking for Iz equals to IR minus IL. Okay, so IL is VL over RL. What is IR? VR over R. VR is V in minus VL over R. Okay, VR here is equal to V in minus VZ. Okay, VL. VZ equals to VL, remember that. So V in minus Vz over R, or V in minus VL over R. So you got your IR. So this one you have, IL you have equation, then you can solve for voltage. Power dissipated Pz equals to Iz times Vz. Okay, let's look at one example of this one. Okay, for linear network of figure 2.22, determine the Vz, Vr, Iz, and Ez. Okay, we need to determine Vz, Vz, Vr, okay, Iz, and Pz. Okay, how do we do? How do we calculate this? Right. Let me copy this, and I'll use my OneNote. So this will be right. Oops, too big. Right. Let's study this. How this thing works. All right. To solve this problem, what is the question? Question one is V Z R. Z V R I Z Z V R I Z. All right. So we have first one. We have to analyze if VZ is on. Okay. Why? VZ is on only when the voltage across is, let's see, let's put higher than or equals to 10 volt because Z is 10 volt. Right? So whatever that exceeds 10 volt, like 11, 12, 15, so it will, VZ will conduct current and it will uh, maintains a 10 volt output. Okay, so that our load voltage maintains at 10 volt. Okay, so we analyze when VZ is on. No, we analyze if VZ is on. Okay, so how to do that? Okay, assume if VZ is not exist or open circuit. So if it's open circuit, it will look like this. RA, RL, and this is open circuit. So you could just actually use the voltage divider. VR V out equals to V in times R L over R plus L. So this one becomes V in is 16, RL is 1.2K, R is 1K plus 1.2K. So what's the total here? Now you gotta press the calculator. Yeah, that's the calculator. So we have 16 times 1.2 divided by, so 1 plus 1.2 is 2.2. So we get the VRL as 8.73. So since VRL equals to 8.73 volts, then in diode is off like an open circuit. So our Vz is 0, and then Iz is 0. What else we're looking for? Vr equals to, how much is it? 16 minus 8.73, which is about 7.3. Okay, 7.3 volts. And then what else? Pz. Also Pz we cannot calculate because the diode is off. Right. Then repeat part A with RL equals to 3 kilo ohm. Okay. So let me copy this. I'll put it here. RL is 3 kilo ohm. So let's do analysis. Step 1, analyze VL when Z is off. So what do we have here? VL equals to V in times RL over R plus RL. So V in is 16, RL is 3K over 1 plus 1K plus 3K. So it's equivalent to 16 times 3 over 4. So it's the calculator. 16 times 3 divided by 4, we get 12 volts. So 12 volt. So does the Zener is on? Yes. The Zener diode conducts. So here, so Vz equals to 10 volt. Oh, sorry. Previously, when I said VZ is 10 volt, is incorrect. Okay, VZ is actually voltage across VRL. So which is basically VRL. Okay, sorry for the mistake. So make sure you get this correction right. So VZ is 10 volt. And then what else do we need? We are gonna for VZ done. VR, IZ, and RZ. So VR, what is VR? Equals to V in minus V out. So V in is 16 minus 10 equals to 6 volt. And then IZ equals to, uh, what is the equation for IZ? We have to use this, not analysis. Here is IL, this is IZ, and this is IR. So to find IZ, let me put the equation. IR equals to IZ plus L. So IZ equals to IR minus IL, which is equals to IR equals to VR over R minus IL is equals to, what is IL? VL over RL, which is equals to, so VR just now is 6, R is 1 kilo ohm, it's correct, yeah. And then VL minus VL is 10. Why VL is 10? Because it's parallel to the diode. So VZ is 10, VL is 10. Divided by RL is 3 K. So if you calculate, you get some values. So basically, IZ equals to 6 milliamps, not plus, it's minus 10 divided by 3K. What's the 10 divided by 3K? 3.3 milliamps. So what we have left, 2.66. Okay, milliamps. That's again. And then we are looking for PZ. So PZ equals to IZ times V. So 2.66 milli times V is 10. What do we get? 26 milliwatt. So that's it, basically. Thirty milliwatts. We get 26 milliwatt. Okay. So power dissipated, yeah, 26 milliwatt, which is less than the specified PZM 30 milliwatt. Okay, so basically this power PZM is a maximum power dissipation for Zener diode. So usually when we want to choose Zener diode, we want to buy it, we have to see the voltage, the power that it can work on. If not, it's going to be a bit hot. All right. So basically, that we have learned about rectifier, whereby the AC coming in to the rectifier. Right? From rectifier output, kalau half wave, if it's half wave, it becomes half wave like this wave signal. And then we have a filter, which is basically the capacitor. Okay, and then we have a regulated voltage, which we cut there. So the regulator is where we use Zener diode. Okay, so that's it for chapter on Zener diode. Okay, question. Why do we have to do two-step analysis for the Zinter diode? Okay, that is question one. Question two. What is the difference between normal diode and Zinter diode in terms of breakdown voltage? Okay, please answer these two questions, write it on a piece of paper and upload it on the quiz section on week 6 in You Learn. Okay, that's all. Thank you.